Hey everybody, back again. In the last video, we discussed the law of reflection, the very simple rule that describes how the ray that describes the motion of a wave reflects off a surface. And we looked at how the law of reflection leads to predict the images we see in a plane or flat mirror. The kind of mirror we're familiar with because we probably look at one every morning when we brush our teeth. Well, now I'd like to look at a different type of mirror, a mirror that's curved, mirrors known as spherical, concave, or convex. You actually probably own one of these mirrors at your house and without even realizing it, but we'll discuss that a little bit later on. So let's get a look at these different images from these different types of mirrors. Now, before we do anything, what I'd like you to do is take a moment and dig through your kitchen drawer and see if you can find a very shiny spoon. Now, if you ever looked closely at your reflection in a spoon, and here the larger the spoon, probably the easier it is to see, you might have noticed that you get a very different reflection depending on which side of the spoon you're looking into. So here in this image, we see in one reflection, the person seems upside down, and in the other reflection, the image is not upside down. Now, why would that be? Well, when your image is upside down, you're looking at the spoon when it curves away from you. The bowl of the spoon is curving away from you. This case, the spoon is acting as a concave mirror. But when the bowl of the spoon curves towards you, that spoon is acting as a convex mirror. So depending which way it curves, you get a very different reflection. Now the question is, how is something as simple as the law of reflection going to explain two different types of images? And that's what I'd like to explore now. So let's start with a spherical concave mirror. Now, the reason why we call them spherical is imagine that I start with a sphere represented by this circle. Well, I'm going to cut a piece of this sphere out so I have a curved surface on which to make a mirror. So here, this half circle actually represents half a sphere mirrored on this inside. And I've marked the center point here, which is the center of curvature of the sphere. Well, so the mirror itself is spherical concave. We call it spherical because it's a piece of a sphere. Concave because it's curving away from you. This center line here is a very important reference line known as the principal axis. And the center point is going to turn out to be important as well. And so I marked the center of curvature. Now this distance between the mirror and the center is equal to 1 radius of the original sphere. Now, if I place an object in front of this mirror, like this candle, the question is, how will the reflected rays create an image? So remember, we only have this simple rule of reflection, that the angle of the incident ray must equal the angle of the reflected ray when measured from this perpendicular normal line. So let's apply that rule to this situation. Well, the first thing to note is any normal line must pass through the center of the circle. Now, here is an incident ray coming from the top of the candle. Where it strikes the mirror, I need to draw a perpendicular line to the surface of the mirror. But this mirror is a sphere, a cross-section being a circle. Now, you may remember way back to geometry class, but any line that's perpendicular to the edge of a circle must pass through the center. That is, any line perpendicular to the center of a circle, it's perpendicular to the edge of a circle, is a diameter line, which by definition passes through the center. So the normal line here must pass through the center of the circle. So when I want to construct a reflection of this ray, I need to measure the same angle below this normal line that I have above the normal line. And here is the reflected ray from this incident ray. all due to the fact that the normal line must lie through the center. Well, I'd like to choose a different incident ray. Instead, I'm going to send the incident ray through this point here on the parallel axis. So again, I'll get started there, click. So here is my incident ray passing through where that reflection was on the parallel principal axis. And again, it strikes the mirror. Well, I need a new normal line. I can't use the same normal line as I did up here because the light's now striking down here. But again, I note that the normal line must pass through the center of the circle. And again, I note that however this ray reflects, I have to construct the same angle below the axis as I have below the normal line as I have above the normal line. So here I have my two reflections, and both obeying the lower reflection, and they cross down here. But this point right here where the reflection crossed the principal axis is a very important point. This point is known as the focal point. The focal point is the halfway point between the mirror and the center is called the focal point. And it represents the point where any ray that's parallel to the principal axis will converge at this focal point. You can also see that the focal point has to be equal to half the radius of the sphere, since it's halfway between the center of the sphere and the edge of the sphere. So keep a note of that focal point because it's a very important point when we figure out these ray diagrams for mirrors. So I want to put all this information together, and it all boils down to basically 3 rules. So let's apply them to figuring out the image of this object from this spherical concave mirror. So I have the object. I am going to start by sending a ray from the top of the candle to the mirror. Now again, I'm not going to bother drawing the normal lines anymore because we know where this ray is going to reflect. The normal line again would pass through the center, and because of that, I saw in the previous screen that the reflection must go through this focal point, which is halfway between the center and the mirror. And that represents rule number 1. So rule number 1 for drawing a ray diagram for spherical mirrors is any ray parallel to the principal axis, any incident ray parallel to the principal axis will reflect through the focal point. And that is our first rule. Well, I know what this geometry is, so what I'm going to do now is I'm going to send a ray from the top of the candle through the focal point. Now, again, we saw in the last slide that if I construct the normal line to the center, I end up reflecting parallel to the principal axis. And that is rule number 2. Any incident ray passing through or from the focal point must reflect parallel to the principal axis. So any light from the object passing through this focal point, when it strikes the mirror, will reflect back parallel to the center line or the principal axis of the mirror. Well, if you remember when we talked about plane mirrors, where my reflections cross has to be where I see the image of where the incident light started from. So in this case, the top of the candle. So that means the top of the candle, of the image of the candle, must be right there. And that will be the image. Now, how do I know it's upside down? Well, let's talk about the bottom of the candle for a minute. If I send light from the bottom of the candle, it's going across the principal axis, which means by definition it passes through the center, which means it is on the normal line. It has no angle of incidence. Well, just as we saw with the plane mirror, any ray of light that passes along a normal line must reflect back along the normal line. That represents our third rule. Any incident ray passing through or from the center of the sphere will reflect back through the center. So that means that light from the bottom of the candle, wherever the image is, it has to be on the principal axis. So if I place the object on the principal axis, the image will be on the principal axis. But Since the bottom of the object is on the principal axis, the bottom of the image is on the principal axis. Since these two reflections down here came from incident light from the top of the candle, that must be the top of the candle image, and I have an upside down image of a candle. Now, this image can be described with several key words. This image is real. That is, the light is physically intersecting at this point. I can pass my hand and actually touch the light. Now, if you remember back in the plane mirrors, the light did not reflect in the the reflections did not cross in the real world. Here they are. Furthermore, not only that, if I actually put a piece of paper at this location in front of the mirror, I can actually shine this image onto a piece of paper. That is why the image is called real. The image is inverted, that is, it's upside down. And it is reduced, that is, this image is smaller than the object. Now, all we did was apply the lower reflection, but because it's a spherical mirror, the lower reflection led to those three rules. Those three rules are incredibly important for determining where the image will form. So let's summarize them on the next screen. So the three rules for a spherical mirror. Rule number 1, any incident ray parallel to the principal axis reflects through the focal point. And remember, the focal point is the midpoint between the center of the sphere and the edge of the mirror. So it's equivalent to half the radius of the sphere. Rule number 2, any incident ray passing through or from the focal point will reflect parallel to the principal axis. Sorry about the text getting chopped off there. So parallel to the principal axis. And then finally, rule number 3, any incident ray passing through or from the center reflects back through the center. That's all we need to figure out what our image will look like when using a spherical mirror. And we're going to see a slight twist on these rules when we talk about lenses later on. So these three rules are incredibly important. You will need them whenever you construct a ray diagram, so it's probably worth your time to write these down on a piece of paper and post them somewhere handy, because you're going to need to refer back to them. All right, I'd like to take these same three rules and apply them to a different situation with the same spherical concave mirror. So, now, same mirror, same concave mirror, but what I've done is I've moved the object much closer to the mirror. The object is now between the focal point and the mirror. It's the same focal point, it's the same center, so it's the same radius of curvature, and the focal point is still halfway between the center and the mirror. So I'm going to use the same three rules, but you'll see that I'm going to get a very different result. So the first step is I'm going to draw a ray from the top of this candle. I will send it parallel to the principal axis to the mirror. Well, that's our rule number 1, and I know from the previous example and the previous rule that this ray must reflect through the focal point. Well, that's good, but now I'm in a little bit of a quandary. Because we're so close to the mirror, I can't send light from the top of the candle through the focal point or through the center. But I can send the light from the top of the candle to the mirror as if it was coming from one of these points. That is, I construct a reference line. Here, this line gives me the direction that if light is leaving the top of the candle, it would be going in this direction towards the mirror. So I can use that reference line to draw my light ray. Now, I'm going to take the reference line away because that's not really a light ray. That just showed me which direction I should send my light ray. Here, the light ray comes as if it's coming from the focal point and strikes the mirror. Now, I know from rule number 2 that that ray will reflect back parallel to the principal axis. So here I have my 2 incident rays. Here I have my 2 reflections. And they do not cross, unlike the previous example when the object was far away. But this is very similar to the situation we had with a flat plane mirror. That is, if the reflections don't cross on the real side of the mirror, I should project them backwards to see if they cross behind the mirror. And just like with the plane mirror, since these two incident rays are light coming from the top of the candle, and the reflections seem to cross there, at this point, I should see the top of the candle. And I do. And I see that my image is virtual. It's virtual because I can't really put a piece of paper here to shine this candle on it. It's behind the mirror. This is the part of the real world. This is just where the image appears to be. I cannot stick my hand behind the mirror. If I put a piece of paper behind the mirror, there's not going to be any light there for me to actually shine an image, make an image with. It's upright because it's not upside down compared to the object. And now it's magnified and not reduced. So I get a much larger image. Now, I mentioned before that you probably have a concave mirror at home. If you use a makeup mirror or shaving mirror to help put on makeup or to put on a tie, you'll notice that these are often called a magnifying mirror. A magnifying mirror is simply a concave mirror where the focal point is so large that when you stand close to the mirror, you are actually inside the focal point. So there you go. It's the same three rules, but they lead to the prediction of a very different image. So one more case to consider, and then the next video, I'm going to do some practice just showing you how to make a ray diagram on paper with a pencil and a ruler. But one more example before we leave concave mirrors behind. What if my object is on the focal point? So I looked at a ray diagram when I was on this side of the focal point. I looked at a ray diagram when I was inside the focal point. What happens if I'm on the focal point? Again, same three rules, so we're just going to apply these same three rules. I send a light ray to the mirror that's parallel to the principal axis, and you guessed it, it should reflect through the focal point. Now, for my next ray, I can't really do it from the focal point because I'm sitting on the focal point. So I'm going to use the same trick as we did before. I'm going to construct a reference line from the center to show me which way the light would be traveling if it came from the direction of the center. So this is, again, my reference line. I want to send light from the top of the candle to the mirror along this line. And again, I take away the reference line because it's not really a light ray. This is the light ray. I just used it to figure out the direction I should send it. And the reason why that's important is because I only have three rules to use. And for this rule, this is rule number 3. Since this incident light seems to be coming from the center of the curvature, it's going to reflect back through the center of curvature. Well, again, I have a situation here where my reflections do not cross. So I'm going to do the same trick. I'm going to project my reflections backwards behind the mirror. But in this case, when I do so, I notice something curious. These two reflections are parallel to each other. That means they will not cross on the real side of the mirror, nor do they cross on the virtual side of the mirror. So if the images don't cross, if the reflections don't cross, there is no image. In fact, what you would see in this case is just a blur. So for a spherical concave mirror, it has an interesting property. If you place an object exactly on the focal point of that mirror, you won't get a real or a virtual image. All right, so it's a little tricky at first, but you'll see that the rules are actually quite simple. You just need to follow them step by step when you're making a ray diagram. Now, we'll practice this on paper. This week, you'll need to do your ray diagrams and upload a picture of your work, since it's pretty hard to do this in a word processor. So be patient with it and take your time. Next week, we'll look at the concave mirrors as well, and also introduce some math, because clearly there needs to be a way to use equations when working with mirrors, and there is, but we'll wait a little bit before we look at the formulas that describe the mirror. So right now, this week, you're only practicing making ray diagrams. Again, it's quite normal if you have any questions or if you're a little confused at first because you haven't done this before. So feel free to send me a picture of your work and ask questions. Okay, see you later.